Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question number 1 asks, how can I calculate the delta G of a reaction? Okay, so question 1. Okay, so first let's define what delta G is. It is the change in Gibbs free energy. So G stands for Gibbs free energy, and the delta always means that there is a change in the values. So Gibbs free energy or the energy used to do work. So this is the equation to calculate for delta G. So delta G is equal to delta H minus T times delta S. So delta H is enthalpy. And delta S is entropy. And T is just the temperature. Okay, so when you have a reaction under standard conditions, then the delta G is equal to the sum of the Gibbs free energy of formation for the products minus the sum of the Gibbs free energy of formation of the reactants. Okay, so under standard conditions, some common compounds have their Gibbs free energy values in a table. So when the symbol has that superscript of like an O, that's how you know that it is under standard conditions. But realistically, not all conditions are standard. So when you want to solve for non-standard conditions, you would use following, where the delta G is equal to the standard delta G plus RT ln K. So R is just the constant. And K is a constant as well. that can be calculated. Okay, so let's see what the junior tutor said. The Gibbs free energy, denoted as G, is a thermodynamic property associated with a chemical reaction. It measures the energy that can be used to do work. It can be expressed as a function of enthalpy, entropy, and temperature. For example, for a chemical reaction to be completed, external energy in the form of heat must be provided by increasing the temperature of the system. This results in a change in enthalpy and entropy. Similarly, the change in enthalpy can be calculated as delta G is equal to delta H minus, I think there should be a T here, T times delta S. Under standard conditions, we can refer to the standard Gibbs free energy of formation, delta GF. Okay, and then under non-standard conditions, the following equation can be used. Yep, so this solution is correct. Okay, so question 2. The specific heat capacity of water is 4,190 joules over kilogram times Kelvin. Its heat of melting is 3.33 times 10 to the 5 joules per kilogram, and its heat of vaporization is 22.6 times 5 to times 10 to the 5 joules per kilogram. For 1 kilogram of water, which of the following requires the most thermal energy input? Okay, so first, so for the question, they give us all these different scenarios where we have 1 kilogram of water, and we just need to calculate all of their different thermal energy inputs and see which one has the highest. So either melting ice at 0 degrees Celsius, heating 1 kilogram of water from the melting point to the boiling point, and then lastly converting 1 kilogram of water to steam at 100 degrees Celsius. Okay, so first I'll just talk about specific heat. So this will help us answer one of the questions. So specific heat can be denoted as C, and it is the heat needed to raise the temperature of a substance by 1 degree Celsius. So by knowing what specific heat is, this can help us calculate for Q. Since Q is equal to mc delta T. So m is the mass, and delta T is the change in temperature, and Q is kind of like the net heat transfer of our reaction. Okay, so basically we need to solve for all of the Q values of the different scenarios. But depending on whether or not you're heating, boiling, or melting, they all have a different way of calculating it. So there's also the latent heat of fusion. So this is energy that must be supplied to a substance or a solid substance in the form of heat to convert it to a liquid at its melting point. Okay, so again, we can calculate Q by doing mass times the latent heat of fusion. And for the last option, we have also the latent heat of vaporization. So this is the energy needed to change a liquid to its vapor state at its boiling point. So the equation to solve for Q is M times the latent heat of vaporization. Okay, so now let's look at all of our different options. For A, we would be using when we melt a solid and turn it into a liquid. This is the latent heat of fusion. So I'm going to write A here, melting 1 kilogram of ice at 0 degrees Celsius. So that means Q is equal to 1 kilogram, which was our mass, and the heat of melting was 3.33 times 10 to the 5 joules over kilograms. So Q is pretty much just equal to the same value, 3.33 times 10 to the 5 joules. Okay, so when we solve for B, heating 1 kilogram of water from the melting point to the boiling point, we would be using the first equation, Q equals mc delta T. So Q is equal to 1 kilogram times C, which is 4,190 joules over kilogram times Kelvin. And then I'll just put my temperature as 100 degrees. So this gives us a Q value of 419 kilojoules. Let me put the second one in kilojoules as well. And then lastly, converting 1 kilogram of water to steam. Q is equal to 1 kilogram times the heat of vaporization, which is 22.6 times 10 to the 5 joules per kilogram. So then Q would be equal to 2,260 kilojoules. Okay, so looking at all our different options, the reaction that requires the most thermal energy input is converting 1 kilogram of water to steam at 100 degrees. Okay, so let's see what the junior tutor said. Converting 1 kilogram of water to steam at 100 degrees Celsius requires the most thermal energy input. There are two types of heat: sensible heat, which involves the change in temperature, and latent heat, which involves the change in phase. Sensible heat can be calculated by Q is equal to mc delta T, and on the other hand, latent heat can be calculated by Q times L ml. Melting 1 kilogram of ice at 0 degrees gave 3.33 times 10 to the 5 joules. Heating 1 kilogram of water from the melting point to the boiling point is equal to 4.19 times 10 to the 5 joules. And then lastly, converting 1 kilogram of water to steam gave 22.6 times 10 to the 5 joules. So that's why C was correct. So this solution is correct. Okay, so question 3. How would you arrange the following compounds in order of decreasing pKa? Okay, so pKa, this can tell us the strength of an acid. So when you have a low pKa, then you have a stronger acid. And on the other hand, when you have a higher pKa, then you have a weaker acid. Okay, so when you have a strong acid, this means that the acid that you have can readily dissociate into its ions and kind of remain in ions in solution. But when you have a weak acid, then the acid only partially dissociates into its ions. So basically, if we look at the question, they gave us different acids, and each of them have a different number of chlorine atoms attached to them. So when you have compounds with more chlorine or electronegative atoms, they are more, or they tend to be more acidic. And this is due to something called and the inductive effect. So basically, since your chlorine is more electronegative, then your protons are donated easier. So if we were to arrange the compounds in order of decreasing pKa, so let's start at high to low. The acid without any chlorines would have the highest pKa. And then this is followed by the acid that only has one chlorine atom, so Cl. And lastly, the acid with the highest pKa is the one with two chlorine atoms. Okay, so now let's see what the junior tutor said. The pKa measures the strength of the acid. The lower the pKa, the stronger the acid. Inversely, a weaker acid will have a more stable conjugate base. The order of increasing stability of conjugate base is, and then they show all the different acids when, so these when they're deprotonated, so that's what conjugate base is. Okay, so then they show the relationship, and then the chlorine atom aids in the stabilization of the conjugate base because it is more electronegative than hydrogen. Thus, it has the ability to induce electron density towards itself that results in spreading out of the electron density of the conjugate base, which we know has a stabilizing effect. The order of decreasing pKa would be the following. Yep, so it's the same order I have as well. I'm just trying to read the description. Okay, so the solution is correct. I'll just also mention the inductive effect. Okay, so question number 4. Draw the electron dot structure of CHClO. Draw the molecule by placing the atoms on the grid and connecting them with bonds. Include all lone pairs of electrons. Okay, so to answer this question, when we write the electron dot structure, we first want to find out the total number of valence electrons. So in the molecule, we have a carbon, which has 4 valence electrons, hydrogen, which has 1, chlorine, which has 7, and oxygen, which has 6. So if we add all of these up, we have a total of 18 valence electrons. Okay, so first, we want to write down our central atom, which in this case is carbon. And then the question also wanted us to place the atoms in the grid and then connect them with the bonds. So I'm going to show what all the bonds would look like and how all the electrons are kind of placed around it. So we have hydrogen, we have chlorine, and we have oxygen. So there is I'll first draw a single bond in between all of them. Chlorine has 6 valence electrons. And notice that the carbon atom doesn't have a full octet yet, so it needs to form a double bond with one of the atoms. So in the case of hydrogen, it only has 1 electron to share, so we know that you can't form a double bond with the hydrogen. The case of the chlorine, it already has a full octet, so it also doesn't want to form a double bond, so that's why we need to form it with oxygen. So I'm just going to show that there's going to be a double bond formed. And now let's count out all the electrons that we have drawn so far. We have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we need to draw 4 more. So they'll just be lone pairs on the oxygen. So if we were to connect all of the bonds, we have a single bond with hydrogen, single bond with chlorine, and then a double bond with oxygen. Okay, so let's see what the junior tutor said. The electron dot structure or Lewis structure is a simple representation that shows the bonding between atoms of a molecule as well as the lone pairs of electrons in the molecule. Step 1, draw the skeletal structure with carbon, which is the least electronegative atom at the center. Step 2, calculate the total number of valence electrons in the molecule. So they did 4 plus 1 plus 7 plus 6 is equal to 18. Distribute the electrons as dots, satisfying the octet rule. Yep, so they also do all the dots around all the atoms. Step 4, replace the 2 electrons with bonds between atoms. Yep, so this solution is correct. Okay, so question 5. Which of the following is not produced through chemical bonding? So chemical bonding this is the association of atoms into ions, molecules, or like different compounds. Pretty much just everyday life, everything is made up of atoms. So let's look at the options that they give us. Adipose fat tissue, so this was formed through chemical bonding. Cells, atoms or the heart. So the answer for this would just be atoms. Yeah, so pretty much everything else is formed through chemical bonding. And atoms are the building block of it. So the Janine The Tutor said that atoms are not produced through chemical bonding. Chemical bond is a lasting attraction between atoms, ions, or molecules that enables the formation of chemical compounds. The bond may result from electrostatic force of attraction between oppositely charged ions, as in ionic bonds, or through the sharing of electrons, as in covalent bonds. Chemical bonding begins with atoms, it does not produce them. So this solution is correct. Okay, so question 6. What do you call a reaction that involves the transfer of electrons from one molecule to another? So these are called redox reactions. So this involves half reactions. So the reduction half reaction and the oxidation half reaction. Okay, so let me just write the definition up here. Involve the transfer of electrons from one molecule to another. Okay, so let's have an example of how we would balance a reduction and oxidation reaction to get a net redox reaction. Okay, so for example, we had xenon trioxide plus negatively charged iodine forms xenon plus iodide. So the first step would be to balance all the atoms that are involved. And we want to separate these into their half reactions. So reduction involves the gaining of electrons, and oxidation involves losing electrons. And we can also tell if a molecule is reduced when its oxidation number decreases, and when a molecule is oxidized, then its oxidation number increases. So in the case of the xenon trifluoride, this is reduced to just xenon. Give myself some space. And we need to balance the atoms. So assuming that this reaction takes place under acidic conditions, when we need to add like oxygen, we would add molecules of water. And when we need to add like hydrogen, then we just need to add some protons. So here our reactant side has 3 oxygens and our product side has none. So to add oxygens, I'm going to add 3 waters to my product side. And now I have 6 hydrogens that are in my product side that I need to put in my reactant side. So I'm going to put my 6 protons on my reactant side. Okay, so that's the oxidation or the reduction half reaction. Now I'll do the same thing for my oxidation. So we have this negatively charged iodine that forms I2. So basically we just need to add a 2 in front to make it balanced in terms of the atoms. Okay, for step 2, now we want to balance out the charges. So we want the charges to be the same on both sides of the reaction. So let's just rewrite it down now. If we look at our reduction reaction, and the reactant side, it has a charge of +6, since we have 6 positively charged protons, and on our product side, everything is neutral. So to make our reactant side neutral, we have to balance out the positive charges. So we're going to add 6 electrons to our reactant side, and the product side just stays the same. So now all the charges are balanced. And let's do the same thing with our oxidation. We have 2 negatively charged ions on our reactant side, and we just have the neutral I2. So I need to add 2 electrons to my product side. Okay, so now that we have the charges all balanced, we want to make sure we have the same number of electrons on both sides. So this is due to the law of conservation of mass. So we want our oxidation reaction to also have 6 electrons. So I'm going to multiply this whole thing by 3. So by multiplying it by 3, this changes it to 6 plus 3I2 plus 6 electrons. So now we can combine both of our oxidation and reduction reactions to write down the net redox reaction. So combining them overall, we write down all of our reactants first. Okay, so 6H plus 6 electrons plus 6 iodine makes xenon plus 3H2O. And now I can also cancel out my electrons since they are present on both sides. And then we are left with the net redox reaction. Okay, so let's see what the junior tutor said. A redox reaction is a reaction that involves the transfer of electrons between molecules. It is a combination of 2 sub-reactions, namely the oxidation and reduction reactions. During oxidation, a molecule which acts as a donor gives up an electron and becomes oxidized. On the other hand, when reduction occurs, the acceptor obviously will gain the electron that the donor loses. Yep, so this solution is correct. Okay, so question 7. What is the standard enthalpy of formation of this isomer C8H18 for a particular isomer? The following reaction produces 5,113.3 kilojoules of heat per molecule or per mole of, I guess this is octane, consumed under standard conditions. And then they give us the balanced equation, so I'm going to write down the same thing. Octane gas plus 25 over 2 oxygens makes 8 carbon dioxides plus 9 H2O gas. Okay, so they also give us the delta H of the overall reaction, which is negative 5,113.3 kilojoules. Okay, so to answer this question, I'll first write down the expression for the delta H of reaction. So this is equal to the sum of N times the delta H of formation of all of our products minus the sum of N times delta H of formation of all of our reactants. Okay, so I can also show what this looks like for our example. So N, that means number of moles, so that's why it's important for your reaction to be balanced, because it has an effect on the overall delta H of the reaction. So starting with our products, we have 8 carbon dioxides. So it's going to be 8 times the delta H of formation for CO2 gas. So it's also important to know what phase your compound is in as well, since depending on whether or not it's a gas or a liquid, then that will also affect the delta H value. So I'm just also going to write the state that all of the compounds are in. And this is going to be added to 9 times the delta H of formation of water. So water as a gas. So those are both of our products. And now I'm going to subtract our reactants. So our reactants is 1 mole of the octane, so I don't need to write any coefficient in front of it. And this is what we are trying to solve for. C8H18 gas. And then this is added to 25 over 2. Delta H of formation for oxygen. Okay, so when we have an element that's in its elemental state, such as oxygen, its delta H of formation value is 0. So I'm just going to cross out this whole part. And now I just need to look up the values for all of the delta H of formations for carbon dioxide and for water. So let me just look it up. So these values are usually given in the question, or they tell you to look at the table for standard enthalpies. So this can be in your textbook or at like the back of a book. So first we're looking for carbon dioxide gas. So its delta H of formation is negative 393.5 kilojoules per mole. I'm just going to write that down. And I'm also just going to show that this should be 8 moles times negative 393.5 kilojoules per mole. Okay, so this is added to 9 times the delta H of formation of H2O gas. So on the table, this is equal to negative 241.8 kilojoules per mole. Okay, so that whole thing minus what we are looking for, which is the delta H of formation of C8H18 gas. Okay, so I can also plug into this equation what was given in the question for the delta H of reaction, which was negative 5,113.3 kilojoules. Okay, so if I simplify this equation and bring our unknown to the other side to make it positive, and then bring the negative 5,000 over to the other side, you get positive 5,113.3 kilojoules minus this whole bracket here. So if you do the math, our moles will cancel out and we get 5,324.2 kilojoules. So now let's just subtract the two and you end up with negative 210.9 kilojoules. Okay, so let's see what the junior tutor said. The heat of reaction, also known as the enthalpy of reaction, is the change in the enthalpy of a chemical reaction that occurs at constant pressure. It is a thermodynamic unit of measurement useful for calculating the amount of energy per mole either released or produced in a reaction. It can be calculated using the formula delta H of the reaction equal to the sum of N times the delta H of formation of products minus the sum of the N times the delta H of the reactants. Standard enthalpy formation of CO2, H2O, and oxygen can be determined using the table for standard enthalpies of different compounds. In addition, since oxygen is in its elemental form, which is the gas, its standard enthalpy is always 0. So it is applicable to all elements that are in its elemental form. So the formula above should look like this. So they have 8 times the delta H of formation of carbon dioxide plus 9 times the delta H of formation of H2O minus what we're looking for, which was the delta H of formation of the octane plus 0. Okay, so then they plugged in all their standard enthalpy values and ended up getting negative 210.9 kilojoules. Yep, so this solution is correct. Okay, so question number 8. What is the name of this compound? So we have a calcium, an H2PO3. Okay, so to name this compound, let's break it up into 2 separate ions. So we have the calcium ion, which has a 2+ charge. And then we also have H2PO3 minus. So this is also known as dihydrogen phosphite. Okay, so now let's kind of put them together to name it. So therefore, our compound is calcium. Just going to put 2 to show its oxidation state. Calcium dihydrogen phosphite. Okay, so the junior tutor said calcium dihydrogen phosphite is an ionic compound. We know this because it is made up of a cation, calcium 2+, and an anion, dihydrogen phosphite. To name an ionic compound, we combine the name of the 2 ions. Thus, the name of the compound is calcium dihydrogen phosphite. Yep, so pretty straightforward. This solution is correct. Okay, so those are all the questions for today. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can leave it a like and comment, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.